There are 6 trig functions that we need to know how to differentiate. We've got our sine, cos, and tan, and their reciprocals, cosec, sec, and cot. I'm going to show you where the differentiation for sine and cos comes from through their graphs, but the other ones, their graphs are a little bit more complicated, so I'm just going to give you the rule. If we start with our sine curve, sine curve starts at the origin and goes high. So we end up with a shape like that. And we covered this in our trig topic previously. If we differentiate this and draw its gradient function, to draw a gradient function we start by finding when it's 0. So flat there and there, and we draw those down and mark those points. So we know it goes through 0 there and there. We then look to see what's happening in the rest. Well, it's increasing there, decreasing there, and increasing there. At the origin, if we draw a tangent line, it really looks like the tangent's 1, and it is for this case. So we can put a line at 1. And then as it goes further here, it's starting to slope further down to 0, so the gradient is decreasing. So it sort of goes like that. And then at this point here is the opposite to before, so it's gradient of -1. And it's decreasing, and it's getting more negative until it goes down here, and then it becomes less negative, but still negative there. So that will come down, look like that, to when it's 0, and then it comes back up again to finish that shape. We had y equals sine x. This derivative is a cos graph. While we're at cos, we may as well look at what the cos graph will look like when it's differentiated. So we follow the same steps. Find when it's 0. Mark those down. Then look to see what's happening in the other points. It is decreasing, the gradient's negative there, increasing there. At this point here, and that point there, the tangent looks like it's 1 and -1. So -1 at the first one, +1 at the next one. And we can draw a curve through that. And we get a sine curve, but it's been flipped horizontally to give us a negative sine curve. So from these graphs, we can see that sine differentiates to cos, and cos differentiates to negative sine. You'll be given a formula sheet in your exam, so you don't necessarily need to learn these, but it's useful to know where they are. And so for the 6 ones that we need to know, y and dy dx, we've got our sine x, cos x, and tan x. Well, sine differentiates to cos x, cos differentiates to negative sine x, and tan differentiates to sec squared x. Later in the topic, I'll show you where that comes from. For our reciprocal functions, we have cosec x, sec x, and cot x. Cosec x differentiates to negative cosec x times cot x. Sec x differentiates to sec x times tan x. And cot x differentiates to negative cosec squared x. we'll go through a few examples to see how this works. So, number 1, differentiate y equals 4 sine x. This is a direct use of the previous rules. So dy dx, we can leave that 4 in front, timesing by. Sine x differentiates to cos x, so we get 4 times cos x, or just 4 cos x. Something a little bit more involved, y equals 4 cos 3x. Now, sometimes there will be brackets around the 3x, sometimes there won't. Either way, it means the same thing. Differentiating this, dy dx equals, we'll leave that 4 in front again. Cos differentiates to negative sine, so times by negative sine 3x. We haven't actually done anything with this 3x, and so we're going to do the same thing we have as applying the chain rule. We're going to multiply by the derivative of that bracket. 3x differentiates to 3. And we can tidy this up. 4 times negative times 3 is negative 12 sine 3x. Number 3, y equals tan cubed 2x. Okay, so for this one, our table doesn't have a tan cubed in the y section, so we should rewrite this as y equals tan 2x to the power 3. And so this is a composite function. And so from before, we learnt that to differentiate a composite function, we differentiate the outer function and then multiply by the derivative of the inner function. So differentiating, bring the 3 in front, leave the inner function where it is, reduce the power by 1. That's the derivative of the outer function done. And now we're going to differentiate the inner function. So the derivative of tan 2x, look at our table, tan differentiates to sec squared x. So tan 2x will differentiate to sec squared 2x. But we would apply the chain rule, times by the derivative of the inside of tan, which is timesing by 2. We end up with 6 tan 2x squared times sec. And if I'm going to rewrite these in the same way, I might as well just put it squared on the outside as well. Now you may be asked for this question, well, what is the gradient dy dx is what when x is pi? So we're just going to substitute into this formula to get that. Now your calculator doesn't have a sec button, so we've got to remember that sec is 1 over cos. So we get 6 times tan 2 pi squared times 1 over cos 2 pi squared. Well, tan 2 pi is 0 and cos 2 pi is 1. We end up with 0. Question 4. You might get asked to differentiate 1 over sine squared 3x. There's multiple ways to do this question, but probably the simplest way is to recognize that the bottom is sine 3x all squared. And so to differentiate, we first need to write this as sine 3x to the power of negative 2. Then this is just like question 3. We're going to differentiate the outer function first and times by the derivative of the inner function. Negative 2 sine 3x reduced power by 1, negative 3. Then times by the derivative of sine 3x. Well, sine differentiates to cos 3x, but then we've got to times by the derivative of inside of the brackets of the cos, so timesing by 3. This simplifies to negative 6 cos 3x all over, and the negative 3 bracket can go to the bottom, sine 3x to the power 3. Finally, question 5. Y equals sec square root x. Now in the past when we've dealt with square roots, we've changed it to x power of half. No reason why that would change here. So sec x power of half. In our formula, sec differentiates to sec x times tan x. So dy dx equals sec x to the power of half tan x to the power of half. And then we've got to multiply by the derivative of the brackets. The brackets that we actually look at is just this one here. So we don't care that there's 2 brackets in the derivative. We're only looking at the one in the original one. The derivative of x power of half is bring the half in front, reduce the power by 1. Tidying this up, we could probably just rewrite those as square root of x's in our brackets. So that's sec square root x tan square root x times by, and we can bring that x to the bottom of the fraction, 1 over 2 x power of a half, which finally gives us sec square root x tan square root x all over 2 square root x. The proofs for differentiating tan x, sec x, cosec, and cot x require knowledge of the chain rule and the quotient rule. To differentiate tan x, we can first split tan into sin x over cos x. That's a quotient. So we'll let u equals sin x, which means that u dash equals cos x, and v equals cos x, so v dash equals negative sin x. That means when we apply the quotient rule, dy dx will be u dash times v, so that's cos x times cos x, which is cos squared x, minus u times v dash, so that's sin x times negative sin x. The negative will make this become a plus, and we get sin squared x all over v squared, or cos squared x. Cos squared x plus sin squared x is a famous Pythagorean identity, which is equal to 1 all over cos squared x. And since 1 over cos x is equal to sec x, 1 over cos squared x is equal to sec squared x, which means that tan will differentiate to sec squared x. Differentiating sec x, well, we first have to rewrite sec as 1 over cos x. Then, we've learned that if something's on the bottom of a fraction, to differentiate it we should bring it to the top. So treat that as if it's power 1, and we bring it to the top by changing the power to a negative 1. Differentiating, we bring the power in front, we rewrite the bracket, and we reduce the power by 1, and then times by the derivative of the bracket. The derivative of cos is negative sine. That means that we have negative 1 times negative sine is sin x over cos squared x. This could be written as sin x over cos x times 1 over cos x, because that would give sin x over cos squared x. Sin x over cos x is tan x, and 1 over cos x is sec x, which, to get the rule that we learnt, we can just change the order of that. We get sec x times tan x. Exactly the same thing can be done with cosec. This time y equals 1 over sin x, rewriting cosec as 1 over sin x, treating that as a power of 1 and bring it to the top. y equals sine x to the power of -1. Differentiating, we get dy dx equals -1 times the bracket, reduce the power by 1, and times by the derivative of the bracket. That leaves us with negative cos x over sine squared x, which can be written as negative cos x over sine x times 1 over sine x. Negative cos over sine is negative cot x, and 1 over sine is cosec x, which if we rearrange that, we get negative cosec x times cot x, which is the rule. Finally, cot x, this is very similar to tan. We're going to start by rewriting cot as cos x over sine x, and then we're going to apply the quotient rule. U is equal to cos x, so U dash is equal to negative sine x. V is equal to sine x, and so V dash is equal to cos x. Applying the quotient rule, we get dy dx is equal to U dash times V, that's negative sine squared x, minus U times V, that's cos squared x, all over V squared, sine squared x. The numerator can be factorized at the negative outside, and we get sine squared x plus cos squared x all over sine squared x. Sine squared x plus cos squared x is equal to 1, so we have -1 over sine squared x. And since 1 over sine x is cosec x, then 1 over sine squared x is cosec squared x, giving us negative cosec squared x.